Look at the time. Okay, so it's just before, we've got until just before 12 o'clock, and I'll give you a 2 minute warning or a 5 minute?
Give me a 5 minute first.
5 minute warning.
5 minutes and then 2 minutes, great.
Brilliant, okay, that's great. Go ahead, Richard. Thank you.
Right, good morning everyone. Really nice to see you all, and thank you much for the invitation, and thank you much to all of you for your time in taking part in this assembly today. So yeah, my name's Richard, and I've been kind of tasked with giving you something of a primer on climate change. What I want to do is kind of provide a little bit of an insight into some of the core science, then move on to a brief exploration of some of the impacts of climate change, and then finish by looking at what are the implications of that? What do we need to do to address the challenge of climate change in terms of climate solutions? So this opening slide gives you a bit of an insight into my background, the kind of things I'm interested in. This is a fragmenting and retreating glacier in Iceland. So I've spent about 25 years as a physical geographer and as a glaciologist. So a glaciologist is someone who's interested in ice. So I work both within glacial environments and environments featuring kind of permafrost. So that's frozen ground. So I spent 25 years largely working in the Arctic and getting that kind of graphic sense of the impacts of climate change within those areas. Yes, I've got very far.
Please, could you slow down a little?
Okay, will do. So starting off by looking at the core science of climate change, something which I guess some people are both familiar with, others might not be. It's worthwhile recognising that the climate has changed throughout Earth's history. And it is changed in response to a variety of different mechanisms and drivers. For example, subtle variations in the Earth's orbit around the Sun. But one of the key drivers of climate change throughout Earth history and up to the current time, up to the modern day, are changes in the atmospheric composition and changes in the concentration of greenhouse gases in particular. So here we're thinking primarily about carbon dioxide as a greenhouse gas, but we're also talking about things like methane and nitrous oxide. So these are all gases that have an impact in the temperature of the atmosphere and the temperature of the Earth's surface.
If I can just, can I ask you just to speak into the microphone, just in case anyone can't hear you?
I will try my best.
Thank you.
Okay.
You can hold it if you need to.
Okay. So if you look at the animation here, let's go back. So we get most of our energy from almost all our energy from the sun. That reaches the Earth's surface. It heats the Earth's surface. That energy is then re-radiated back out from the Earth's surface back out to space. But a significant part of that energy that's being radiated from Earth back out to space, so-called terrestrial radiation, is absorbed by the greenhouse gases, and then it kind of contributes to this warming within the atmosphere. And an element of that natural greenhouse effect is essential for life on Earth. Without any greenhouse gases whatsoever, the average temperature of the Earth will be minus 19 degrees C. So an element of that is really is important for life to exist on Earth. But there is a clear connection between the concentration of greenhouse gases, atmospheric temperatures, and indeed human activity that has been established for well over a century, and that's one of the things I want to kind of convey. The science of climate change is nothing new. It's been around for a long time. So just an example, Svante Arrhenius was a Nobel Prize winner in chemistry going back to the start of the 20th century, and in 1908 he said the slight percentage of carbonic acid, what he was referring to there was carbon dioxide, in the atmosphere may, by the advances of industry, be changed to a noticeable degree in the course of a few centuries. And the people at that stage were looking at the combustion of coal at the start of the Industrial Revolution. So people going back to the 19th century were already making the connection between the combustion of coal, the release of carbon dioxide, and the potential impacts that would have on global climate. So what we have here is that human activity, primarily is extracting sort of fossil carbon, so we're thinking of here coal, oil and gas in particular, burning that, so it's the burning of those fossil fuels which is the primary reason why we're then releasing carbon into the atmosphere, so that's then increasing the carbon dioxide levels in the atmosphere. We've also got deforestation, widespread kind of chopping down of trees and the burning of those trees. So that's the other main route. A large part of that carbon dioxide which is going into the atmosphere is then reabsorbed either into the ocean, where it contributes to the ocean acidification, as another issue, or it contributes to, to photosynthesis. It lays down new biomass. But ultimately, we're still in a situation where, of the order, there's a net transfer of carbon from these sources, from these different activities, about 4 billion tonnes per year is being added to into the atmosphere. And we see that in terms of the changes in carbon dioxide levels. So these are showing carbon dioxide levels in the atmosphere over the last 800,000 years. We can extend it this far back because you can actually record the amount of carbon dioxide in bubbles in ice cores in Greenland and Antarctica. And you can see these natural fluctuations which have taken place. These are through the glaciations that we've had in recent Earth history. But the thing to point here is that when we see the impacts of human society, this dramatic increase in carbon dioxide levels within in particular the last 70 years. And that is such a precipitous rise, you can't really even resolve it on the figure. It appears like a vertical line. So that's humans coming on the scene and then start, rapidly, in particular, burning fossil fuels and releasing those into the atmosphere. So we can see this dramatic rise in carbon dioxide levels and these changes in atmospheric composition.
Can I just ask you to explain on that graph what are the numbers on the side? And
Sorry, yes.
What are the numbers at the bottom?
Yeah, so these are years. These are basically going from the present day back in time. So going back about 800,000 years. So this is going back into the first half of what's known as the Quaternary period. That's the most recent phase of geological history. And this is a geological time period which has been marked by fluctuations in climate related to the glaciations, for example. This is the most recent phase of Earth history. This is the concentration of carbon dioxide within the atmosphere in parts per million. So we're currently at 426 parts per million. Basically, that translates to about 0.04% of the atmospheric concentration at the moment is made up of carbon dioxide. Doesn't sound like very much, and it isn't very much, but that small percentage is enough to have a significant impact on the absorption of that outgoing sort of heat energy from the Earth and to contribute to that warming. So, what about the impacts of this? Well, the impacts of climate change are becoming increasingly obvious both on a local and on a global scale. I know I'm going to try to limit the number of graphs that I have, but this is another one which I think is important to bear in mind. This is, again, it's showing time on the x-axis. I know this is small, but you all have copies of these slides that I've kind of provided to the presenters. I'm happy to pick up on any questions that emerge, after the event.
Sorry, could you slow down speaking slightly again?
Will do. Sorry. So what we have here is we've got time. This is showing this time the last 2,000 years, and this is going from 1850 to 2020 here. And this is showing temperatures. Just follow the pattern. You can see this is related to an average of 1850 to 1900. So if we look at the first sort of 1,000 years or so, it was a bit warmer than that average from 1850 to 1900. Then it drops a bit. We go through what's known as Little Ice Age, but then you can see this dramatic rise over the course of the last 150 years or so. This sort of pattern is known as the hockey stick graph that you might have heard of. And then on the right-hand side here, we're going from 1850 to 2020 up to the modern day. We can see this rise in temperatures. This blue line is showing what models suggest that this is what the temperature would do if the climate was being driven solely by natural forcing, driven solely by things like sunspot cycles, or was being driven by volcanic eruptions. So you might see this little dip here. This little dip here is a little change in climate, for example, related to the eruption of Mount Pinatubo in 1994, which has cooled down the climate. But the only way in which we can explain the observed increase in temperatures within recent decades is by incorporating the impacts of human activity and of that change in greenhouse gases. So this blue line is ignoring the changes in atmospheric composition. this is including that. So we need to include that to be able to explain the changes that we've seen. So if we come even more towards the sort of modern day, we just look at the last sort of 50 years or so, we can see there's just been this progressive increase in temperatures. Again, this is expressed against this pre-industrial average, to the extent that last year was the first year that was over 1.5 degrees C higher than this pre-industrial average. And the significance of that 1.5 degrees C is something I'll come back to at the very end. And we'll get away from some graphs for a while. You'll be pleased to hear. You know, in terms of the impacts of that, to start off with, we see a greater incidence and severity of extremes in temperature. So you'll remember back, you know, a couple of years ago, that it was the first time in recorded history in the UK that temperatures rose above 40 degrees C. You know, we have the longest history of recorded observations of temperature in the UK of anywhere in the world. In Oxford, it actually goes back to the 1600s, and it's the first time a temperature of 40 degrees C was ever recorded over that instrumental record. I suppose most recently we can think about the fires in Los Angeles. You start to think about loss and damage related to climate change. You know, and in particular, you know, the destruction of over 10,000 homes and some pretty high-value homes as well. Again, the impacts of climate change here. This fire took place at the end of a prolonged drought, and then the problem was that the wet season that they typically get, or almost invariably get, at the start of the winter, just didn't happen. It didn't appear. So you've got a correspondence then with the winds that they get in winter at the end of a prolonged drought, then kind of contributed to the severe weather event. And I was looking, estimates this morning are that the economic costs of this are about the order of $250 billion, almost $250 billion, so immense economic damage associated with that. More locally, as the atmosphere warms, we have more in the way of moisture, more in the way of water vapour that can be held within the atmosphere as it gets warmer. So we then get clear evidence of the increase in the incidence and severity of heavy rainfall events and the impacts of flooding, which of course is a key concern in relation to Cumbria as we think about the impacts of events like Storm Desmond in the past. And I think for me, again, I think back to some really dramatic and again record-breaking storms that take place in the European Alps. I'll just let this sort of play out. This is some footage from the Italian Alps showing the runoff during the storm event, and these were, you hesitate to use the phrase, but pretty apocalyptic in scale, to the extent that they're now talking about actually abandoning some of the valleys of the Upper Alps because of the severity and the magnitude of some of these severe storm events that are taking place in the summer.
Was that water?
Yes. Yeah. So as I said, I've been interested in glaciers. This was a seminal moment in my life. This is me as a nipper, probably about sort of 10 or 12. This is the first time I ever saw a glacier. This is a Grossglockner in the Austrian Alps. And I've just become accustomed in my lifetime to going back to glaciers, and they will have retreated. And even over the small fraction of my lifetime, majority of the glaciers I've worked on have retreated several kilometres over that timescale. And I think what surprises us as glaciologists is we're not just now in an era of glacier recession, we're in an era of glacier extinction. We're in a situation, certainly in the European Alps, the glaciers are retreating and the Alps is deglaciating more rapidly than anyone had really predicted. If we end up thinking about the loss of ice, the same thing is happening with things like the last remaining ice sheets, the Greenland ice sheet. So where that meltwater then ends up going into the world's oceans. So the key concern there is sea level rise. We've had about 0.4 metres worth of sea level rise. If Greenland was to entirely fail, that's going to take place over a long period of time, but that would be 7 metres of sea level rise. So even if we're looking at a metre of sea level rise, these red areas provide predictions of parts of southern Cumbria, and you can see around Lancaster those areas that could be inundated by that sea level rise. So I just wanted to kind of finish by talking a little bit about the our response to this, and people will talk about carbon budgets. You might have heard people talk about the importance of 1.5 degrees C, and also net zero, and what's net zero all about, and why is there the focus on net zero? What emerges is that there's actually a pretty straightforward relationship. Again, the axis along the bottom here, this is looking at the cumulative carbon dioxide emissions since 1850. You can see that's the start of the Industrial Revolution. And this on the y-axis shows the warming. And there's actually a pretty good linear relationship between the cumulative amount of carbon dioxide that's emitted into the atmosphere and the amount of warming. So this is tracking the historical changes in the historical warming as we've emitted more and more carbon dioxide cumulatively over that time period.
Richard was 5%. Can
Right.
I just check? I just want to make sure I understand. When you say cumulative, do you mean all the carbon that's...
It builds up. It builds up in the atmosphere. Carbon dioxide sits around in the atmosphere. It doesn't get removed from the atmosphere very easily. It's got a long resonance time. So as we emit year on year on year, it's additive. It builds up over time. So here we're not looking at annual emissions. We're looking at those emissions building up over time. And that's the big challenge with carbon dioxide. And these are predictions. These SSPs as to how society might evolve in the future. The best case scenario is we go hell for leather and being more sustainable, and we manage to limit total carbon dioxide emissions to here. In which case we limit warming to 1.5. But if we carry on the sort of business as usual, then we end up as here. We're already towards 2.5 degrees C of warming by I think this is by 2050. The reason why there's a focus on 1.5 degrees C is because of concern related to so-called climate tipping points. There are a variety of different parts of the Earth system where if the temperature goes below past 1.5 degrees C, it triggers events that once they're triggered are irreversible. It is an immaterial what we do. We cannot stop that. So if I just pick out a couple of examples, I've mentioned things like the collapse of the Greenland ice sheet or the collapse of the West Antarctic ice sheet. If we go towards 2 degrees C, we risk the inevitable collapse of those ice sheets and the sea level change that occurs. But working in permafrost environments, then I want to just flag one up here. Permafrost is frozen ground. So I've worked in the Canadian Arctic. Before 10 years ago, these features didn't exist. What you're looking at here is what people have called a retrogressive, a mega slump. This is where the ice under the surface has been exposed by heavy precipitation, heavy rainfall, and then the ice melts out during the summer, and it causes these massive slumps, which are then associated with the release of more carbon out into the atmosphere. So we've got large-scale sort of destabilisation of the landscapes in these environments, and these didn't exist 10 years ago, and they are expanding at an exponential rate. So what do we need to do about it? Quite simply, what we need to do about it is to bend the curve. We need to reduce the amount of carbon emissions, carbon dioxide emissions in particular, that we're releasing into the atmosphere. This is our trajectory of carbon dioxide emissions. This is total amount of greenhouse gas emissions. This is including methane and other greenhouse gases. This is what we need to do to reach the targets agreed in the Paris Climate Agreement. This is where the current policies are. This is where the current pledges are. So there's an increasing gap between where we need to be and where we are going at the moment. Finally, just when people talk about net zero and reaching net zero, what do they mean? Imagine that our total carbon budget that we have to limit warming to 1.5 degrees C is literally like a bucket, and it's almost full. The key thing we need to do is to decrease the rate at which we're filling in the bucket, but what it also recognises in net zero is that there will always be some residual emissions, some emissions that we can't really deal with. So what we can do there is support the kind of processes that will naturally suck that carbon out of the atmosphere and store that within soils, within trees, or maybe within geological stores. So that's why people talk about net zero, is you reach net zero. The residual emissions that were left after you've made all of the, and that's where the focus should be, on reducing emissions, is then balanced out by enhancing the ability of the natural environment to store that carbon. So again, impossible to read, and hopefully this will be useful in your slides, but this is just tries to highlight all the various different climate solutions. The key thing we need to do is to reduce the sources. So we need to do things like use more renewable energy. We need to think about things like reducing food waste. We need to do things like making more, buildings more energy efficient, and that's been an exciting thing to get involved with work with Kathy and Cass and the team, getting involved with the retrofit work. But at the same time, we need to do what we can do to support the sinks. Things like the protection and restoration of ecosystems, for example, and we see that work locally in areas like Skiddaw Forest and around Haweswater as well. So just to kind of summarise the key points, the science related to this is not new. For over 150 years, scientists have known that greenhouse gases in the atmosphere have affected the Earth's temperature. It's in the last 70 years in particular that we've seen human activities in the release of greenhouse gases really being the predominant driver of climate change. The impact of that is becoming progressively more obvious in both locally and globally, and that's entirely consistent with what models predict. If temperatures increase to 1.5 degrees C for a prolonged period of time, we don't know, but potentially for a number of decades, then there's a risk of triggering these climate tipping points, by which stage we'll then be passengers. We won't be able to reverse that. And so ultimately to limit the risk of dangerous climate change, we need to reduce the amount of greenhouse gas concentrations in the atmosphere, primarily by reducing emissions, but also by supporting things. So thank you very much for your attention, and I'm very happy to do what I can to try and answer any questions that emerge, both now and also via sort of subsequent correspondence and email. Thank you.